Hey, Jakob.
Hey.
Cool. So it's a pleasure to introduce our last speaker. It's Jakob Uszkoreit. Jakob is the co-founder of Inceptive, which designs RNA molecules for vaccines and therapeutics using deep learning to make RNA-based medicines more accessible. And for those who maybe don't know, Jakob was at Google for more than a decade, and he kind of knows a little bit about transformers since he was behind the groundbreaking "Attention is all you need" paper. And so we're really excited to have you here to tell us what is maybe not so great about transformers. We've heard all these talks today about how transformers are like amazing and, you know, you should just go use them and have fun. And I think here we're going to get some kind of cold water maybe on board. So looking forward to it. And if you want to stream your slides, but you don't have slides, right? You're going to do it in the background, right?
Exactly.
Awesome. So we'll be here, and I'll probably jump in at various points when there's questions.
Please do. Thank you for the introductions, and thanks for having me. I should also add, that paper was actually a really fun collaboration with a whole bunch of people, each of whom was absolutely necessary for this work to come out this way. I learned a ton on the way, and I'm incredibly grateful to have had that opportunity to work with that bunch of people. But it is true, actually, that I'll try to find some cold water. I think I may have found a little bit. I should add as a caveat that this is not built like an academic talk, so it's a bit different from talks that I gave at conferences or so, in that it certainly is full of bold claims and has absolutely guaranteed insufficient evidence for pretty much all of them, I think. And so, believe at your own risk. So far so good. People often say, if it ain't broke, don't fix it. I think it's actually an incredibly useful, often very useful engineering mantra. But there's I think an alternative sometimes, or an alternative mode, which is if it ain't broke, well, let's try to break it. Let's see what's wrong with it. Can we find kind of from first principles reasons why something that isn't broken actually, or doesn't seem to be broken, actually is failing in certain ways. And so maybe the subtitle to this talk could be something like 3 great reasons we should replace the transformer, and you would have never guessed number 3. And so since this is enough, or these were enough attempts at making jokes, even in the first 3-4 slides, the rest of the talk can be very serious. But maybe taking a step back, let's talk briefly about this kind of whole premature optimization versus first principles thinking, which I think is actually, premature optimization is really what this "if it ain't broke, don't fix it" tries to prevent. And I think that sometimes this idea of first principles thinking, Elon Musk talks a lot about it on and off, is potentially kind of a workaround in a certain sense, preventing you from, doing optimizations or going into a certain direction that you wouldn't necessarily have to go. And so, as an early example, I actually remember one time, as a preschooler. You know quite a bit of stuff as a preschooler, right? From experience, a lot of it, some not from experience, right? But you've probably learned that moving heavy stuff is hard. And you've also learned that explosions are really dangerous. And you've learned that they look like giant fireballs. Not all of this is true. And generally, at least I experienced that remote controlled cars are fast and awesome. And then the first time I kind of, somebody tried to explain to me how combustion engines work. There was this head-scratching moment, because what I heard was, well, cars are generally kind of built around this giant hunk of metal, and that giant hunk of metal is really only there because in the middle there are like small spaces in which there are explosions, and they're contained by this giant hunk of very heavy metal, and that tries to then channel all the force of these explosions into moving, an even bigger hunk of metal that is basically carrying this giant hunk of metal. That is the engine. And at least at the time, that seemed like a fairly backwards way of doing this. Obviously, I had no idea about kind of the energy in fossil fuels and all of that stuff. But it did seem odd. And I think it's actually not that different from the thought process that many years or decades later actually was what started this transformer project. Because we did start with a few kind of first principles assumptions, namely, maybe most importantly, that it is possible or likely possible to compute good representations of some chunks of sequences in parallel. And what inspired us there most, I guess, is really that it seems like, those tree structures that linguists often talk about when they, try to formalize kind of the statistical dependencies between words and text are actually kind of largely right. So I personally believe they're almost never exactly right, but often, largely. And what that directly implies is, if indeed those statistical dependencies are often approximately tree-structured, then it should be possible to compute reasonable representations of chunks of text, for sure, of sequences of words in particular, in parallel before you then kind of join these parallel threads of execution and then aggregate maybe new, more global representations from that. And another assumption we made is that training speed is actually really what is most crucial for model quality at the end of the day. And that the key bottleneck, at the time at least, was basically the length of the longest sequential computation. And so we kind of placed this bet that parallelization actually of this kind of sub-representation computation might be able to buy us much more than the computational cost that we had to expend in order to effectively marginalize out the dependencies, meaning basically assume all dependencies, right? So one interesting thing that this self-attention mechanism employed in every layer in the transformer does is it basically actually considers all pairs of stuff, right? And so in a certain sense, you could say it considers all dependencies, all possible dependencies, marginalizes those out, much more expensive than say considering only the true one, if there was such a thing and if you knew it, but seemingly worth it if as a result of that you can actually massively parallelize. And so in my mind, at least, that process was pretty similar kind of to maybe what made me scratch my head about cars and combustion engines, cars with combustion engines many years prior. And effectively, the latter 2/3 of this talk I'm going to try to spend on a few maybe general areas in which I'm scratching my head about transformers in that same way.
Can I barge in?
Please.
So this is a super nice historical kind of context about the origin of the transformer architecture. And I was wondering if you could expand a bit on the thing about this first principles approach, because I would say, at least for myself, it was kind of surprising that you could kind of remove the sort of somehow temporal nature, which as humans, when we read text, we tend to read, say, left to right or right to left, depending on which language you speak. And I was just kind of curious, was this something that you at Google kind of figured out from linguists, or it's it was really taking a different perspective on the problem?
Okay, so it is a somewhat different perspective. There was a linguist involved. Well, actually, there probably were a few linguists involved. For me personally, the linguist that was involved most was my dad, computational linguist. So I had no choice. Right? The kind of a problem that runs in the family in a certain sense, and so, but it wasn't just what I took from him and others wasn't just the fact that there's maybe this kind of often largely approximately right tree structure, but that in fact our ways or this model of thinking of language as something that is sequential is overly indexing on our representations of language. And so when we communicate, when we talk, we largely say words in sequence, except then we often insert fillers and we also, often do this and so forth. So we interrupt ourselves the entire time. It's not exactly sequential, right? We do jump back. Yes, it's not like we can just fill in things, but we try, I think. And when reading text in particular, we actually can jump back. And I'm not an expert on this stuff, but as far as I know, it is not true that we always read in order. So probably, I mean, necessarily you can show we read more in order than not, because we eventually end up at the end of something, right? Of some long string of characters or words. But as far as I know, humans tend to actually jump back and forth a lot. Now that said, yes, we could go by the limitations of our own cognitive apparatus, but if we have a different one, and this makes a big difference, and probably I should have mentioned this, that actually, what we were optimizing for wasn't software that runs on some accelerators or some silicon of our choosing. It had to run on the accelerators we had, and they looked, largely like the ones that we still have today, except the ones today are even faster because they're evolving so fast. But they are just insanely good at doing these independent, simpler computations in parallel. And so if you really wanted to kind of improve utilization and what you could squeeze out from these accelerators, it just seemed to be the right direction to improve parallelizability. So that might be different from how you want to, or from how humans have evolved to process language, and probably is quite different, right? But yeah, it's just different hardware or whitware that has different strengths and weaknesses.
Awesome. Thanks for the context. And please carry on to tell us all the problems.
Okay. So right before I get to all the problems, I did want to spend maybe 2 more minutes or 3 on why overall I personally would think it actually helped. And really, I think the key thing is this computational efficiency, specifically on today's typical accelerators. But there's another reason, and that has nothing really to do with the specifics of the model or the architecture, but really that once in a while, when something different comes along, it helps with momentum, right? It helps with competition, friendly and all, but still, it really just helps to get people to contribute new, fresh ideas, or get people excited about stuff. Even if initially that excitement sometimes is disbelief or so, right? Or, like I said, friendly competition. So it was like that the other way around. We had Facebook's convolutional seek-to-seek paper that, that we in our what we thought last stretches of readying attention is all you need, that we first read that it came out then, and that had pretty good results. And so certainly, that nobody knew at the time, but that certainly pushed us and motivated us and so forth. And I think similar things happened afterwards. And in terms of momentum and fresh ideas and contributions that got people excited, Sasha Rush has this amazing The Annotated Transformer post, which when I saw it was just amazing and just really, really fun to see people do that kind of stuff. And I think that actually is often underestimated as contribution to kind of the community's reaction is underestimated as a contribution to what kind of makes this work or made this work in a certain sense. Okay, so nothing else? Well, there's this one other thing, and that's actually that decoupling the architecture and the parameters of the model from what you could call maybe the registration of the elements of the structures that the transformer ingests or produces actually allowed very easy adaptation to new and different input and output modalities, different kinds of structures, right? And effectively what it kind of did was it generalized this absolutely revolutionarily powerful seek-to-seek approach to something that's maybe a bit more like stuff to stuff, right? So technically you could say, oh, it's set to something, and then, or set to set, maybe even if you drop a bunch of, if you drop position representations and so forth. But ultimately, if you can encode the topology, if you wish, or the registration of these elements, right? These individual positions, or as they were called initially, that the transformer works on, then you can apply it fairly generically, not always efficiently, but fairly generically, and that in turn, made this guy show up. and with them, like this horde of other Muppets and friends and family of Bert. Initially, I guess, focused on language really, but then also spilling into vision and into this really, really impressive flurry of activity around self-supervised pre-training. So there was generative pre-training, which also uses the transformer in a maybe in quotes more traditional way, but exploiting this kind of flexibility, around the input and output structures that need not necessarily just be sequences in that sense anymore, but anything you could encode in a set somehow. Just broadened or increased the efficiency of some of these self-supervised approaches, specifically masked or mask style, denoising autoencoders and related approaches. This has touched a whole range of different applications, including now biochemistry. So there is now prop BERT and DNA BERT and amino BERT that play a role in all sorts of different applications around or in proteomics, and also provided a great segue for me to kind of put in a shameless plug, maybe speaking a little bit to some of the things that we do at Inceptive, at least, which is, as you heard in the introduction earlier, we're designing RNA, and specifically initially at least mRNA molecules that we try to design such that they have improved properties in desired ways, such as improved stability, that you might not have to deep freeze mRNA-based therapeutics or vaccines anymore, or that they might last much longer if you do. Higher protein expression, which could render it more effective and maybe applicable to a broader range of diseases. And it's just a fascinating, huge search problem with just ginormous spaces. So, even for the COVID mRNA vaccines, for instance, you have 10 to the 630 synonyms, mRNA sequences that would actually produce the same protein in our cells that we want produced for these vaccines. But it's also an incredible predictive modeling challenge, right? We don't understand most of these properties, meaning we don't understand how they work, and we don't even know if we know all the mechanisms. In some cases, we know we don't know all the mechanisms that kind of give rise to these properties or that impact them. And so we have very little hope of generating enough data in our lab for each of these properties of interest. And so really, self-supervised pre-training is at least one of the pieces of the puzzle that we hope to be applying in order to tackle problems around RNA therapeutics and vaccines.
Can I barge in again? Sorry. So this question you mentioned about we don't really understand the properties of these molecules. I mean, wasn't chemistry sort of solved by chemists in some sense, like 100 years ago? Could you maybe sort of expand a bit on what the challenges are?
Yeah, sure. So I'll try to be quick because there's still a lot coming. But basically, kind of true, yes. Chemistry kind of solved, but I would say there are aspects to some of these macromolecules, some of the biopolymers, RNA, DNA, that are not exactly kind of small molecule chemistry in the sense that, just like proteins, their structure, their 3D structure, their arrangement in space really makes a difference. And it can affect chemical properties, right? So depending on the arrangement, on the geometry, effectively, of the bonds relative to each other, you seem to get different behavior when it comes to things like hydrolysis that eventually degrades these macromolecules, for example. But that's just the chemical side, and we're definitely interested in that. But there's also the biological side, and there it gets even crazier because in the environment of cells, for example, right, there is an unknown set of players, some of which we know, many of which we don't, of enzymes, of proteins around that effectively have highly non-trivial effects on the properties of these molecules, like their biological stability, how long they last in cells, how much protein they express, and so on and so forth. So none of these properties really are kind of a function of just the molecule itself in question, but really a function of any number of different molecules around, which I guess also explains why end-to-end, very large-scale deep learning, has maybe seems like a worthwhile thing to try. Whether it's going to work or not for, say, the specific application, of course, we don't know yet. There's some good indications that it can be useful, as we saw through AlphaFold and I guess some of the proteomics models that I mentioned earlier. But yeah, I guess the proof is still in the pudding.
Awesome. Thanks for clarification.
Sure. Okay, so with that, back to these first principles I was alluding to earlier, and how I personally think the status quo might actually be broken right now. And the first kind of cluster of issues that I see revolve around data, and this is maybe also the most important, given that data seems to, at the end of the day, always be the one thing. It's the one thing that always matters. It's not always the only thing that matters, certainly, but it definitely, machine learning is the one thing that always matters. And I guess I'm in good company with opinions like this, right? So Thomas tweeted a little while ago, a few years ago, I was mostly interested in models. Over time, he's seen his interest shift to data. And, it seems like we're slowly maturing. I agree. I do think it's a bit cyclical. These things go back and forth. When a revolutionary approach comes along, and promises and delivers, like deep learning, massive improvements, then that becomes, for quite a while, tends to become the, if it works, like it did in this case or does in this case, becomes the area of most or a lot of attention. But then what we've seen in the field a few times already is that as the rewards you reap by applying those methods and improving them start to slowly plateau, you can come back, you can usually come back to data in order to further improve stuff. And one interesting thing that I find odd is that, we still haven't found ways of end-to-end learning from samples from only the input or only the output distributions. So there are these highly, highly effective, but also pretty expensive pipeline heuristics. I would call them heuristics, like back translation or noisy student and lots of related methods that effectively use learned models that are learned on smaller amounts of labeled data, so input-output pairs, in order to then turn either samples from only the input or samples from only the output distribution into input-output examples. And sure, you can do that, and it works great with some drawbacks, but still, it doesn't seem right. And there are architectures, in fact, several. One in particular I worked on together with a bunch of people called Kermit, that can be trained on input examples, output examples, and input-output paired labeled examples. But so far, it's not like they've actually shown even remotely the same kind of improvement as some of these, in quotes, heuristics. And I find that pretty odd, and that's definitely kind of a fairly obvious head scratcher in the sense that we see this data can help, but end-to-end in kind of end-to-end simplistic or simpler architectures, not pipelined schedules or so forth, we haven't been able to really reach the same improvements from that data. A slightly maybe more involved situation that is also very common, actually, is that we're still not able to learn end-to-end from unaligned data. And so there are many problems out there where the vast majority of training data, machine translation probably being the most prominent, where the vast majority of training data today actually comes from was produced by automated systems that were given ginormous amounts of input and output examples, but separately, input and output, not aligned. But knowing that there should be alignable pairs. And so in machine translation, for instance, work that I was involved in back in 2008 already, were recently far improved stuff, actually a variety of papers, have basically proposed these pipeline systems where you have one step in which you say, for instance, mine the web as a collection of unaligned monolingual documents, and you try to identify documents that are translated or that should be paired as training data for translation. And you do so oftentimes using a trained translation system or something quite similar. There's also been huge progress in unsupervised machine translation, which makes this assumption, right, that those links are not known. But that's all of those approaches are fairly specific. All of the ones I know of are fairly specific to machine translation. And so what I haven't seen yet, and I'm confused by that, is a generic approach that applies across MT, but also question answering. There should be tons of questions out there that also have answers somewhere out there on the web that should be pairable, and comes with different problems, but also shares, I think, a lot of the problems that machine translation training data mining has. Image descriptions is a similar one. There, I maybe see more of a reason for why we're in that situation, right? We've only recently started to really use training on otherwise unstructured, organically created descriptions or of images, alt texts, and similar in a way that really improves over the state of the art trained only on labeled data, certainly for image classification and object detection and friends. But still, it should be possible to get more data this way. And the list of problems for which this, at least I think, seems to be true, is actually quite long. Maybe again, kind of a specialization or an extension. Well, an extension of this could be that it need not be the case that they come from the same modality, right? So usually today, labeled examples for one task, say translation, for instance, right? They're specific to one set or one pair of modalities. So there is now end-to-end. There's end-to-end speech-to-speech translation systems, and there are text-to-text translation systems, and so on and so forth. But a translation system that gets better if you show it, or when you show it, pairs of text, pairs of spoken translated sentences, pairs of images that depict, have half translations in them. Say, for instance, you take a photo of a restaurant menu in one language, and then the translated version in another language, where instances or pairs of in all of these modalities actually improve one and the same system. And this is despite the fact that transformers have actually helped along the convergence of architectures across modalities. And I think one of the reasons why we've not seen this, certainly not much, is that oftentimes these joining these modalities in single models is done by effectively, adding heads that are then specific to those modalities. And unfortunately, we haven't yet figured out how to engineer these heads such that they only take care of things that are specific to the modality they're responsible for, and not of anything else. And that seems to be, I think, a remaining challenge that could address kind of this observation that we currently can't seem to be learning well from examples in different modalities, or the union of many examples from many different modalities each. But maybe kind of as an aside to this, how about multiple instances in a single modality, right? So instead of saying, we have text-text translation pairs, and we have spoken language translation pairs. How about we have, for some of those texts, multiple different versions, right? So we have maybe multiple ways of phrasing the same input sentence or the same output sentence. We have multiple ways of pronouncing a similar input or a synonymous input or output sentence. How about using all of those together at the same time? There is some interesting evidence from machine translation and speech recognition, actually, that this should help quite a lot. But if you look at things like computer vision problems, where it is also not uncommon that we have many images of the same scene or the same object, there it seems much less obvious how to actually then combine those in an elegant way. And I think actually, ultimately, my intuition would be that it hints at an underlying, more fundamental underlying problem that I'll try to kind of get closer to later in the talk. Okay, so we're technically already at the time I wanted to use initially for just the presentation. So I'll hurry up a little bit. and maybe largely skip over this part, but it is also odd that in many problems or for many different tasks in computer vision and elsewhere, but in computer vision it's particularly pronounced, there are probably multiple different sources of data that could be particularly informative for learning models for this task. And one crass example is effectively things like, say, object detection, where clearly, today most of those models are trained on two-dimensional annotations. Well, maybe annotations also, labels also in the 3 dimensions, but from annotations of two-dimensional inputs, images, or sometimes video. But and plus some semantics, plus some labels, along with bounding boxes. But they don't actually ever consider non-semantic data describing geometry, even though it's actually relatively cheap to obtain this, right? So, unlabeled samples of fairly complex 3D geometries, obtained through LiDAR, can actually be created at fairly low costs. And I would say intuitively, if a model that tries to do object detection understands a ton about, not about semantics of objects in the real world, but about their geometry of common objects, right? What do cars, what's the shape cars generally have? What are the shapes bicycles generally have? That should help. But actually, so far, that doesn't seem to be something that we certainly not commonly do. And it also seems like pre-training for this kind of very orthogonal data that you want to jointly be able to learn from might not be quite the right paradigm. And so, maybe to sum up the data part, there's been amazing progress around pre-training and fine-tuning in this general paradigm. But transferring things across modalities still typically involves what I would call Franken models. So these are models where basically, depending on the modality, you turn some piece on and some other piece off, and you basically swap out pieces of the network more or less as deterministic functions of the modality of your input or the modality of your output. And as a result, but not only because of this reason, we're far from being able to utilize all the data that intuitively would seem relevant to a given problem. Say, like an object detection, we're not utilizing 3D geometry data. And given that data is by far the best overall, I would say, and most reliable way to improve models, that strikes me as a bit weird. And from first principles, I would say there's a lot of potential for changing things out. We'll get back to this at least a little bit later. But another area is indeed still efficiency. And I said earlier, well, transformers improve parallelization or parallelizability of some of the computation of representations of pieces of your input or effectively your output. And that's true, and I think that's really the single biggest reason why they help in many cases. But I actually think potentially the single biggest kind of source of inefficiency, if you wish, still largely remains to be tackled. And so, non-autoregressive machine translation made a lot of progress. Diffusion models have very recently made really impressive leaps. It's actually one of the really fun things for me to on occasion look at back in largely computer vision land or graphics also is what people are doing now with diffusion models. I think it's really cool. Addresses some of the aesthetic issues and also practical issues of autoregressive models very well. And in fact, if it wasn't for diffusion models, there would have been at least a fourth and maybe a fifth reason why we should replace transformers in this talk. But yeah, then despite global receptive fields that these transformers have, at least for many modalities, we actually know that the information stays largely local. So there's a paper by Lena Vojta and a few others that look at representations as they evolve throughout layers in transformers. And it seems like information doesn't travel that far, even though we have this global receptive field where every piece of your input or representation or your representation at least can talk to any other piece in every layer. And there's some obvious reasons for this, or more obvious reasons for this. One is the omnipresence of residual connections that provide a very strong bias. for keeping representations, roughly aligned with the locality or the registration, say in sentences, the position of a word that representation is computed for. But this also means that we allocate our compute resources approximately uniform across this registration, across, say, for example, if you consider images or video, spacetime. And okay, that doesn't sound like a terrible idea until you look at this image. And if you currently feed this image into a CNN or a vision transformer, it doesn't matter. Most of the flops expended look at blue sky, and only a small minority of them actually look at the bird and what kind of bird that might be. And that seems wrong. It seems bad enough for this image. But if you consider video with a non-moving camera, then this is actually true for most of the pixels, most of the time in most of the videos, approximately, at least, minus some noise and maybe minute movements and so forth. But certainly for video, this seems to be a real source of inefficiency. And that's simply that the relevant information for any given task in these modalities, the relevant information content is often clumpy, because that's how the world is. And this is true, at fixed resolution, fixed sampling rate, so fixed frames per second with a fixed resolution. It's certainly true, and sometimes much worse, otherwise, say when you have point clouds that are distributed very non-uniformly in space and space-time, well, space. And there have been some end-to-end approaches. The perceiver is an interesting one that try to tackle this problem, but so far they don't seem to be particularly efficient. They solve some of the issues, but they don't seem to be a real kind of complete answer to the efficiency aspect of this problem. And so, to me, that I can't help it, but to me this smells like compression, right? The problem smells like it could be solved by compression. And so we know that utilizing lossy compression schemes that are actually aimed at human perception, not machine perception, can help quite dramatically. We've known it for quite a while. So could we just learn compression schemes suitable across a variety of tasks? And how would they be, if at all, different from today's learned representations that our neural networks evolve kind of layer by layer? Well, one key difference would be that they should either get faster over time as training commences, or they should spread information more uniformly as basically as training goes by and as the model gets better. And I think ultimately it in some way necessitates a change to the way we currently train these things, in part because we expect the sizes of things to change, right? So if we want to get the speed up, then the input size has to change. The input shape can't be constant. If we want information to spread more uniformly, then again, I would say one can argue that in our current kind of fixed batching scheme and so forth paradigm, this can't happen. Now, as I prepared this talk and prepared the slides, and in fact, this just happened earlier today. I was looking for one particular reference that highlighted one aspect of this problem, and had to ask Alexei Dosovitsky, with whom I had the opportunity to work on the vision transformer, and who's actually now at Inceptive as well, and asked him for this reference, and he didn't come back with a reference. He came back with the paper that hit arXiv on November 3rd that I hadn't seen. So much for arXiv sanity or insanity, that actually for at least some image tasks seems to provide a pretty good solution that basically is along these thoughts and ideas. So yeah, look for that. It's pretty neat. I think I haven't read it in detail yet, but yeah. So maybe this is not one of those cases where from first principles it's still broken as of November 3rd. Okay, and so the last one that I'll have time, the last kind of block of things that I think are broken revolve around symbols, objects, this kind of stuff. And this is a super complex topic. I'm definitely not going to do it any kind of justice. Thankfully, there are some great reviews like the one from Klaus Greff and friends. But basically, the specific kind of potential area and currently active area of symbolic-ish object-laden representations that I would like to talk about shares one thing with all the other kind of instances of objects or symbolic-ish techniques in deep learning. Namely that my overly simplistic view of them is that they really are merely efficiency hacks that we should learn, and that they don't do us any good really, other than speeding stuff up. Now this is definitely a somewhat controversial opinion, but if we look at only symbols in say input and output representations, it's not too difficult to make that claim at least a little bit. Okay, so a thought experiment, right? Usually we represent text, for instance, as a sequence of tokens, maybe down to characters or so, right? But this actually comes at a significant cost in expressivity. We take this for granted, but we certainly can currently train text models that understand this thing. Not in full, at least, right? Maybe if you were to now kind of add formatting tags and stuff like that, maybe for this case it would work. And maybe you could claim, okay, fine, but that seems kind of unimportant, super rare, and whimsical, right? But then let me ask you, why is it that I can only have new emojis once a year? And why do they have to be selected by some committee? Right? We recently had this case actually in practice where there's a DNA emoji, but there's no RNA emoji. So we thought, oh, can't we make the claim now that RNA is something, mRNA in particular, that's on everybody's mind? Can't we just ask them to get us an RNA emoji? And we were about 3 days too late for the deadline, and reaching out to the Unicode consortium didn't help. I understand why and so forth, but there are definitely some drawbacks to requiring these kinds of organization that stem ultimately from the fact that we want to use symbols to encode this stuff. And it gets pretty bad once you leave kind of the Latin script dominated parts, and you encounter that, yes, in fact, there are scripts to this day where proper typesetting on computers doesn't really work. Mongolian, I think, is an example of that. To be honest, I don't know exactly how common the phenomena are that are not well expressed in today's typesetting systems. So I can't really kind of estimate the gravity of these issues, but it's definitely the case that we're losing out in terms of our richness of representation of things like text by using these kinds of symbols. So what if, instead of doing that, we presented it across many tasks in a more generic form? Say, as the pixels of an image into which we've rendered the text. And that's something that we've actually tried for machine translation and wrote a little paper about a while ago, Alman. But obviously that's terribly inefficient, right? So now instead of using these symbols that we hand engineer, like emojis, like Unicode at the end of the day, now we have pixels. They usually require, you need many more pixels, certainly if you want to express kind of these rich formatting and graphical phenomena. And so with today's machinery, that's terribly inefficient. But let's assume for a second, we actually had some really efficient learned and compressed implicit representation. We could potentially get it down all the way, or not all the way, but fairly close to kind of those symbolic representations. And they might actually remain richer. And it's not entirely clear that we couldn't, in some cases, go below that, because text also tends to be compressible, even losslessly. And so actually, it seems like this idea that effectively seems obvious for images and video might even ultimately help with efficiency if it's applied to text, at least if you have it in sufficiently large amounts. So to make a very long story and very, very kind of hypothetical story somewhat shorter, I wonder what would models look like if we reduce the reliance on external symbolic representations, on hand-designed, crafted symbolic representations, at least for input and output. And if we compensated for the efficiency loss by generically or with generically learned dense implicit representations, and then on the way, increasingly unified, use this kind of transition to increasingly unify the shapes of different modalities. Right? So we've now said that maybe images and text should or could look very much alike. I don't know exactly what this would look like. I have some guesses, but they're definitely too half-baked to put them even on these slides. But maybe we could also apply this to other modalities as well, and then maybe even this multiple heads, input and output heads Hydra problem would go away, right? Could we then actually just stuff this all into one single giant neural network, not one where individual pieces have to be turned on or off depending on what the modality is at any given moment, but where it's really just the same very dense, highly optimized architecture, same set of parameters. You might not even need elements anymore, or maybe they're always canonical, right? They're kind of fixed length up to a certain degree or fixed size. So anyway, I wonder what that would look like. And I actually feel like, maybe using at least some of these, as half-baked as they all are, observations and quotes, first principles, head-scratching moments, to inspire thought about ideas around what those models could look like, I personally think could be quite interesting.
Awesome. Thanks a lot, Jacob. That was a super nice talk. It's not every day that we get to see the kind of like deep questions, about transformers being exposed this way. So very nice. I think we have time for a couple of questions. There's one which is perhaps a little bit technical, but let's see how we go. So it's there's a typo, but can transformers be used to find which code snippets in one language are similar to another? So if you've got Java and Python, and do you think graphical neural networks would be a solution? And I think what this question is getting at is a little bit this thing about like you emphasized a lot machine translation and alignment and this kind of stuff. And do these problems also occur when we deal with source code?
Super interesting question. So let me think. Basically, so I would say, the simple, straightforward answer is yes. Transformers could definitely be used for something like this. One interesting question is, how would you define what it means for snippets of code to be the same? And a very pragmatic definition that one could potentially operationalize for creating data around this is to run the code and see what happens. And if you then end up with either the same result or the same behavior, in quotes, then maybe you, at some point, if that happens often enough, you want to say, yeah, these are reasonably similar. And in the process of doing this, basically generate instances, increasing numbers of instances, and instances of potentially increasing complexity, right? If you start doing this for single instructions and then you add stuff, you might even with fairly unguided search procedures get to a stage where you can just create training data for a model that then might look like something like a seek-to-seek model, but it could also look like these I guess, what do you call them? Siamese or two-tower models that are effectively trained to compare different instance or input representations for multiple instances. GNNs in particular are basically making use of the fact that code has this much more stringent structure than natural language or observations of the natural world around us. I think, certainly in many cases, I could imagine could help with efficiency. Would it dramatically transform our ability to identify whether these two things, whether two code snippets are the same? That I'm not so sure about, because ultimately, whether they're the same or not, I guess, doesn't have as much to do with, say, their abstract syntax trees and how those relate to each other. Where the crispness of GNNs would help, as it does with the semantics of the code. Right? The subtle issues are you call two different library functions, they're defined to be mostly the same except for some subset of the inputs, and hence you ultimately have to, if you want to do it just from with zero other knowledge, you basically have to figure this out. Ultimately, I guess also made further problematic because there are many different ways of computing any one thing, and as a result, even going all the way down to executed instructions on a given CPU or so, or a given chip, whatever it is, might not actually conclusively answer your question unless they happen to be exactly the same. Right? So if they compile to the same bytecode or the same natively executed instruction sequence, sure, then you can, but I don't think that's a likely event.
Cool. And
Okay.
maybe one more question. Yeah, thanks a lot.
Sure.
One more question would be, in this sort of landscape of challenges you mentioned, so things with symbolic representations, lossy compression, and so on, which of these do you think is like let's say, the most important, so to speak? If you had to rank somehow these problems, which ones keep you awake at night, maybe is the other way of putting it.
So I actually think they all are. I really think that they all are, not exactly, but they all are roughly different sides of the same coin. So our difficulties in learning, interchangeably from different modalities, they stem from the fact, I think, maybe overly simplified, but I think they largely stem from the fact that we have this heads problem, that basically we don't have a neural network into which we can actually input these efficiently, without swapping out some sets of parameters or maybe some kind of structural pieces. And so that you could address by having in a certain sense, a representation at a meta level that is able to express things in all of these modalities, and that you could get by learning kind of these compression schemes if you learn them across many different modalities, and hence, I guess I also think that ultimately our only way of potentially getting rid of these symbols, which yes, I think they currently, they are very pragmatic heuristics for improving efficiency, but we don't know how optimal they are, and they're certainly not sufficient in order to express everything we'd like to express. But I would guess they're not optimally efficient either. And there again, I think having these kinds of learned implicit representations is a reasonably good kind of general direction for trying to address the potential inefficiencies, but also kind of broaden or increase the expressivity of models for some of these modalities. And so, in a certain sense, I think they all kind of belong to each other. Doesn't mean that and it's certainly unlikely that the easiest or kind of the most direct potential solution for addressing any single one or any single very specific subset of these, that they would at all look similar to each other. That I don't think is the case. But maybe kind of in the limit, if you want to generally solve all of these, it might be that actually they share one and the same solution.
So are you sort of telling us that the future may involve some sort of not maybe radically different architecture, but some that there is life beyond transformers in some sense?
I actually think the architectures will increasingly get simpler and simpler and simpler, and they will increasingly look very much like. I mean, you'll be able to tell the architecture from the hardware it runs on, and so. Ultimately, I think to me personally, the big lesson that I learned in the vision transformer work is that these patches that we use there have nothing to do with the images. They're not chosen based on the image. They're fixed. So why is it that some patches work better than other patch sizes and so forth? It's because they have slightly different computational trade-offs. It has nothing to do with the nature of the images, as far as I can tell. Maybe in extreme cases that could happen. You could imagine certain distributions of images and certain kind of patch sizes that just make it harder or make it easier. But by and large, across kind of the universe of images and the universe of possible patch sizes, or the space of possible patch sizes, what matters, I think, is how well they are suited to the underlying hardware. And so my guess is what we're going to see is that the architectures will look more and more boring, which I think is great, because architecture engineering tends to be this kind of, black magic alchemy that more often doesn't work than it does. And ultimately, I think, basically we'll use more and more uniform necessarily, will necessitate more and more similar and uniform representations that have. Where, for instance, also the relation between representation size, if you wish, and compute budget becomes much, much less direct. Right? So right now, if you want to expend more flops on the same image, right? Take more patches of the same size, and you're going to do exactly that. And then that doesn't get better, at least from our experiments. That doesn't seem to get better, because somehow your additional patches now overlapping or whatever add kind of more, in a certain sense, more interesting detail. It just gets better because you add more flops, as you would kind of expect. But that it shouldn't be that kind of your way of computing your initial input representation, if you want to think about it that way, is kind of the screw that you use in order to adjust the expended compute up or down. If anything, it should be kind of how information rich given the task or for the task a given input might be. And ideally, ultimately thinking of us humans, a little bit at least, maybe what really should necessitate how much compute you spend is how much time you have. If I have a ton of time to compute the answer for a given input, take the time. I mean, assuming the energy comes for free and in a sustainable manner and so on and so forth. But why not take longer? But if you have to make a decision really quickly because the product calls for it in that situation, ideally the model is able to at least give you a reasonable guess in much less time, with much less compute. And so I feel like that's what we should actually strive for, like anytime algorithm style inference, if you wish. Anyway, so yeah, long story short, I think architectures will hopefully become less boring and just ideally suited to the hardware they run on, and in a certain sense, the remaining work to get us there is I think in figuring out how to unify and how to make effective and efficient the representations that we use.
Awesome, thank you. I think we've run out of time, so thank you once again for sharing your deep knowledge with us and the community. And yeah, it's been a pleasure. So I hope,
thanks again for listening.
Hope next time we ask you, all these problems are solved.
Well, we'll see. I mean, given that paper that came that I only just saw earlier today that came out on November 3rd, who knows with that pace.
Great. Thank you very much, Jakob.
Thank you.
Thanks.